All right. Continuing with our study of conditional distributions, we're going to talk now about conditional distributions in the case of bivariate normal distribution, which is an extremely important and widely used situation that arises in statistics often because, as we'll learn in a later chapter where we talk about the central limit theorem, that's where the central limit theorem is what makes the normal distribution so ubiquitous and such a reasonable assumption in many applications. And so the normal distribution arises in a lot of statistical applications. And as we mentioned last time, conditional distributions arise in applications because we're often conditioning on data. So how do we do conditioning in the case of the bivariate normal distribution? So by definition, we call a pair of random variables jointly normal if any linear combination ax plus by is normal distributed for all real numbers a and b. Okay, so that's the definition. And so let's suppose x and y are jointly normal. And let's assume that their mean 0, variance 1. And let's assume their covariance is rho, some value rho. Then we can ask, what is the conditional distribution of y given x? So how are we going to do this? Well, let's define a new random variable w to be y minus rho of x, rho times x, I'm sorry. And first observation should be that x and w are jointly normal. Why? Why? Because if you let c and d be real numbers, then cx plus dw equals cx plus, by d times the definition of w is y minus rho x. This can be expressed as c minus d rho x plus dy, which is normal because x and y are jointly normal by assumption. Okay. So x and w are jointly normal. The expectation of w is the expectation of y minus rho x, which is the expectation of y minus rho times the expectation of x. Both are mean 0. So this is 0. The variance of w is the variance of y minus rho x. The variance of a sum of random variables in this case it's variance of y plus rho squared variance of x minus 2 rho covariance of xy. Covariance of xy is rho, so we have variance of y plus, oh, I'm sorry, variance of y was assumed to be 1. Variance of x was assumed to be 1, so it's 1 plus rho squared minus 2 rho. Let's see, what did I mess up here? Oh, it's 1 plus rho squared minus 2 rho squared. What did I mess up? This is right. We have 1 minus rho squared for the variance, and then the covariance of x and w is the covariance of x with y minus rho x. Bilinearity of covariance tells us that this is covariance of xy plus covariance of x times minus rho x. This is rho plus, well, rho, and the rho comes out, rho minus rho times the covariance of x with itself. Remember, covariance of x with itself is the variance of x, which we've assumed is 1. So this is rho minus rho, which equals 0. Okay, so this tells us then that x is independent of w. We will show this later. So if normally distributed random variables are uncorrelated or have 0 covariance, that means they're independent. That's not true in general for all random variables, of course. Uncorrelated does not mean independent, but it does for jointly normal random variables. And then given the value of x, the conditional distribution of w is normal 0, 1 minus rho squared. And the conditional distribution of y given x is equal to x is, well, we can write y as y minus rho x plus rho x, right? Y is equal to w plus rho x, right? So given x is equal to x, y is equal to w plus rho little x, which is normal with mean rho x variance 1 minus rho squared. So then what this tells us then, in terms of statistics or prediction, is that if we observe that x is equal to a value little x, then we should predict that y will equal rho times x. And the margin of error in this case is the square root of 1 minus rho squared, which is the standard deviation of y, the conditional distribution of y given X. So this is how we would do these calculations in the case where we have jointly normal random variables. We've also introduced some concepts here that we'll explore in the next video of conditional expectation and conditional variance. So what these are saying is the conditional expectation you can think of is the expectation of the conditional distribution. The conditional variance is the expectation of the conditional distribution, is the variance of the conditional distribution. So in other words, that's exactly what this is saying here, which is that given that X is observed, we expect Y to have the value rho times X. That's our new expectation. Our initial expectation was 0, but we update our expectations based on the value of X. That's incorporating the dependency of Y on X. And so this is something that we can, in general, do pretty much for joint distributions of, jointly distributed random variables of all sorts. And that's something that we will discuss more in the next video.